So the immune system is a really important part of your homeostatic balance in maintaining a defense against any kind of pathogens that are going to try to come in and cause havoc in your body. There are two key ways in which your body defends against pathogens that are trying to get in. One is called non-specific defenses or innate defenses. These are pretty much broadly effective against any kind of pathogen that tries to get in, more of a generic kind of system. Then there is the specific defense system or the adaptive system. This one requires having already been exposed to the pathogen, and it only will protect against a particular kind of pathogen as soon as it, for example, a virus, if you got immunized against the flu or you had the flu, you're specifically protected against that kind of flu, and if it changes just a little bit, you're no longer protected against it. That's the specific defense system. So the non-specific defenses, there's kind of a broad range of non-specific defenses. The first and probably most important one is just a barrier. If the pathogens can't get into your body, they can't cause any kind of problems. So your skin is by far the able to defend against the greatest amount of pathogens. It's able to defend because you've got tons of layers of dead keratinocytes. They've got a ton of keratin in them that's a really tough protective layer. It's pretty dry, it's pretty nutrient poor, it's not a great place to survive. There are also chemicals present in the sweat, sort of the layer on top of your skin, that are able to even kill some of the pathogens that land on your skin, that get to your skin. And sweat has a component called lactic acid, which is sort of acidic and able to stop bacteria from growing that well. That said, you still have a lot of bacteria growing on your skin, and we'll talk more about the bacteria that you find all over your body and their important roles at another time. Even the parts of your body where there isn't thick layers of skin, all of your opening cavities are lined with what are called mucous membranes. So they also have stratified squamous epithelium layers, and the mucus that's on those layers will trap microorganisms, and there's enzymes present in that mucus that will destroy bacteria as well. So skin and mucous membranes as a barrier just to things getting in your body are called the first line of defense and the easiest way to stop things from getting in. If something has breached those barriers and gotten beyond your skin and your mucous membranes, there are classes of cells called phagocytes. You may remember that phagocytes are funky, cool cells that can actually take their outer cell membranes and like blob around something. They surround it, engulf it, bring it into their cell, and then destroy it. So different phagocytic cells that you find really involved in the immune system: neutrophils. Neutrophils get to sites of injury really early, and they're capable of phagocytosis. Macrophages are found in various guises in pretty much every tissue throughout your body and are capable of doing that phagocytosis thing. Eosinophils are also really important phagocytic cells. Mostly they work with antibodies in adaptive immunity, so we'll get back to eosinophils later. Another really cool kind of cell are called NK cells. NK stands for natural killer cells. So these cells, NK cells, can non-specifically tell that a cell is abnormal. It's either been infected with a virus or a bacteria, or it could be a cancer cell. And the NK cells then somehow move their Golgi apparatus around to the side of the cell. So their Golgi apparatus gets moved around, and then they make tons of vesicles full of these proteins called perforins. They release the vesicles onto the surface of this cell, and the perforins make holes in the surface of the abnormal cell, and then that cell sort of like loses all of its contents, ooze out of those holes, and the cell just goes whoosh, and oozes down into this like little nothing, gets killed. Natural killer cells, so cool. All right, so say you get injured. Say this is the easiest way, right? I get a splinter in my finger. Any kind of damage, could be that, could be you're playing sports and you wrench your shoulder and you tear something in your shoulder. That kind of damage will trigger a release of chemicals, inflammatory kinds of chemicals. These chemicals have a lot of different jobs, but one of their jobs is sort of triggering what we call inflammation, or the inflammatory process. Some of the things, two key processes that they can trigger are diapetesis and chemotaxis, as well as margination. So chemotaxis is just the process of chemicals being released that actually attract other cells to that area. Margination is wherever these inflammatory chemicals get released, the capillary beds that are going through that area become, the cells within those capillary beds start to stick to the wall of the capillary beds. So they're like start crawling along the edge of the wall, and then they can actually do this process called diapetesis, or they can actually change their shape and go from like kind of a round blood cell, and they flatten out and actually squeeze out of the capillaries. So big cells capable of leaving capillary beds, which they normally can't do in response to the inflammatory chemicals. So the process of inflammation, you've got some kind of damage that has released these chemicals. Generally, there are mast cells in the area, and the mast cells release the two chemicals histamine and heparin. You remember the jobs of histamine and heparin. They will trigger dilation of the blood vessels and increase flow to that area. So you've got increased blood coming there, and then the cells in that blood are marginating to the edges and then using diapetesis to get out of the capillary beds into the local area. Some of the cells that are attracted are phagocytes, particularly neutrophils. Neutrophils are actually kind of known as the first responders. So they'll come in, you know they're capable of phagocytosis. Neutrophils are also kind of kamikaze cells. So when they get into an area of inflammation, they can actually, commonly they will essentially explode, destroying everything in their surrounding area by the release of reactive oxygen species. So they use sort of a process of just creating this mass destruction. So you've got neutrophils that are just killing everything in their area, trying to make sure that whatever triggered the inflammation gets destroyed and gets out of there. So now you've got this huge mess that the neutrophils have created, killing everything. And then really the next step of the neutrophils have kind of killed everything in the process. And then other phagocytes, particularly macrophages, will come in and phagocytize all of that debris, clean it up, and then fibrocytes in the area can sort of rebuild the tissue, whatever it was, or if that tissue isn't capable of regeneration, just create a fibrous scab kind of there. Okay, so that's the process of inflammation. Generally, inflammation in a local area will tend to destroy the pathogens, keep it local, and kill off whatever it is, and then your body's safe. We all know that the process of inflammation can go on. You hurt your shoulder, the inflammation starts, and instead of being contained, it can go on and on for a long time, creating damage that can cause long-term problems. So there's always this balance, homeostatic balance in inflammation. You need some inflammation or you're going to die of these pathogens coming in. But too much can create all kinds of problems as well. So the balance is really important. Another process, so inflammation is one sort of process that can kill off pathogens that invade. Another process is called complement. So complement is actually a pathway of a bunch of proteins that tend to be just floating around in your bloodstream under normal condition unless they're activated. And there's two key ways to activate it. The most common way, called the classical pathway, is that antibodies from specific immune system, and we'll get to that in a little while, antibodies can actually tag a cell as foreign or bad and trigger, when an antibody binds to something, that triggers complement to come in. The complement proteins bind to whatever the antibody activated, and they can do a bunch of different destructive things. They can do kind of the NK cell thing. They can form a pore in the membrane of a cell. So literally start this hole that will cause the whole cell to like collapse. They can make it more likely to be phagocytized. This is called opsonizing it. So when they opsonize it, the complement proteins are basically tagging it, saying, hey, 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 phagocytic cell, come over here, eat this thing, it's bad. They can also trigger mast cells that will bring inflammation. So complement can actually be a part of getting inflammation to start. So the alternate pathway does not involve antibodies, where in fact complement proteins can actually be activated by foreign stuff in the plasma in the absence of antibodies, bind to the cell wall and do any of these things, form a pore, bring in phagocytes, or start inflammation. We've talked about the physical barriers. We've talked about different kinds of phagocytic cells, the different ways that natural killer cells can find something and kill them. Interferons are a class of proteins that are part of that whole inflammatory process that tend to work best on viruses. So they can trigger, they find cells that are virally infected, and they can trigger inflammatory processes. We talked about the complement system, talked about inflammation in general. Another thing that can help mobilize your immune system are fevers. So in fact, there are specific proteins called pyrogens that can increase your body temperature. And this is a pretty good thing because higher body temperature can actually make a lot of these proteins involved in the inflammation process work better. So the fever will actually make inflammation happen better. So short term, the fever can actually be really good at jump-starting and making the non-specific innate parts of the immune system more effective.